Hello there. Today we're going to learn about inductors. To introduce this topic, let's look at a couple of examples. So what we have here is a battery that's attached in parallel to a light bulb. That light bulb can be treated as a resistor. And that is also in parallel with a wire of very negligible resistance. There is a switch that is currently open, so no current is currently flowing through the circuit. So what do you think would happen if we close the switch? Will the light bulb light, or will it stay unlit? The answer is that the light bulb does not light. Now that's because the light bulb is a resistor and the upper wire has negligible resistance. Because of this, the light bulb will remain unlit since most of the current will follow the negligible resistance path through the upper wire that shorts the circuit. Well, that was a good warm-up. Let's try another question. Notice what's changed about this circuit. The upper wire has been replaced with another wire, and the only difference about this wire is it's been coiled with a number of coils. So this upper branch in this circuit is a coil of wire, also called a solenoid, and it is of negligible resistance. Currently, the switch is open, and this upper solenoid is in parallel with both the light bulb and the power supply. So what do you think would happen to the light bulb if you close the switch? Will it light or will it remain unlit? And don't forget that upper coiled wire has negligible resistance. Believe it or not, as soon as you open the circuit, the light bulb will light brightly, but then it'll get dimmer in time. And that is in contrast with the previous example. In the previous example, we just had a straight wire shorting the circuit. And we would think that this coil of wire in this example would short the circuit too, causing most of the current to bypass the light. But that doesn't happen. Since the light bulb is a resistor, though, one would expect the bulb to glow only very dimly when the switch is closed, because most of the current should follow the low resistance path through the coil of wire. But what happens instead is that when the switch is closed, the bulb burns brightly and then gets dimmer. This is actually due to the coil's ability to store magnetic potential energy based on Faraday's law and the change of magnetic flux. Okay, so that might have threw you for a loop on this one. No pun intended. Well, let's see how you deal with this next example. Here we have the same circuit, but the switch is closed. The upper branch in this circuit is a coil of wire of negligible resistance. The bulb is unlit, and the switch has been closed for a very long time. What happens to the light bulb if the switch is now opened? The bulb is unlit because with the switch having been closed for a very long time, the upper coil of wire, which has negligible resistance, shorts out the light because most of the current will go through that negligible resistance wire. Because remember, most of the current takes the path of least resistance. So that makes sense that the light bulb will be unlit. But now we open the switch. And as soon as we open the switch, we discover something. That the light bulb burns brightly, but then it quickly goes out. The reason for this is that when the switch is opened, there is a change of magnetic flux through that coil's wire. And due to the coil's ability to store magnetic potential energy, it provides energy to the circuit to allow the light bulb to light for a brief period of time before going out. This coil of wire has a very important function in circuits. We call this coil of wire an inductor. An inductor is a conducting coil used to store potential energy in the magnetic field that it generates. Now, the circuit symbol for an inductor is just a series of loops, like a coil, as you see here. And that's because if you were to actually open up a circuit device that has an inductor in it, you would literally see loops of wire, usually wrapped around an iron core. The interesting property about an inductor is that an inductor will resist changes to the current running through it, generating an EMF to oppose changes to its magnetic flux. Now, this relies on what we've learned before with Lenz's law and Faraday's law. So let's walk through a sequence of events to help us understand how an inductor works. Let's take this inductor. So the upper image is just the side view of the inductor. The coil is coiling away from you from left to right. And the bottom image is just the axial view of the inductor, looking at it as if you were peering at it from the right end. The first thing to note is that an increasing current in this inductor creates an increasing magnetic field along its central axis. So notice how we have current going from the left side of this inductor to the right side. Now, as you curl your fingers around the coil using the right hand rule of your right hand, your fingers curl away from you, causing your thumb to stick out to the left. That's the direction of the magnetic field. And since the current is increasing in this inductor, so does the magnetic field that the inductor generates. Now, looking at it edge on, notice how the current is increasing in the clockwise direction, as you can see from the bottom image. Now, here's the thing. An increasing current causes an increase in the magnetic flux of the coil. Lenz's law states that an induced current in the coils will oppose this increase by creating an opposing magnetic field. So notice that the original increasing current is going from left to right. That increasing current causing that change of magnetic flux induces a current to oppose the change. And that induced current then will be going from right to left. And that induced current generates its own magnetic field. And notice how this magnetic field goes from left to right. This magnetic field opposes the original increasing magnetic field. Because remember, according to Lenz's law, an induced current will be created that generates a magnetic field to oppose the change of magnetic flux. Since the original magnetic field was going to the left, as you can see here, and that magnetic field is increasing, getting stronger and stronger in magnitude, the induced current is generated that creates a magnetic field to oppose the increasing current. So notice from the bottom image, the increasing current is circulating clockwise around the inductor, while the opposing induced current circulates counterclockwise, producing a magnetic field that's coming towards us. Now, the induced current will carry positive charge carriers to the left. And now that we have a separation of charge, this establishes a potential difference across the inductor. So notice this potential difference. This potential difference is going from the high potential on the left side to the low potential on the right side. And this is due because of the induced current that causes the charge separation in our inductor. So to summarize, with this increasing current creating an increasing magnetic field, causing an increase in magnetic flux, there is an opposing current that tries to counteract the increase in magnetic flux. Well, now let's look at a decreasing current. A decreasing current in the solenoid creates a decreasing magnetic field along its central axis. So notice the current is still going from left to right. The magnetic field is still pointing to the left, away from us in the bottom image. But the difference here is that the current is decreasing in magnitude, getting smaller and smaller. So that means the magnetic field is getting smaller and smaller, which means the magnetic flux is getting smaller and smaller. According to Lenz's law, there will be an induced current that supports the inductor's decreasing current. So notice how in this image that we see that the decreasing current going from left to right, but we know it's decreasing, so that current's getting smaller. So an induced current will be created to support the original current to help keep it from decreasing as fast. So the induced current in this situation is in the same direction as the original current, while the induced current when we had the increasing current scenario was in an opposite direction. So the induced current will always be produced in a way to oppose the change in magnetic flux. So because the current was decreasing, the magnetic field was decreasing. And because the magnetic field was decreasing, the magnetic flux was decreasing. This induced current will then generate a magnetic field to support the decreasing magnetic field of the inductor, thereby opposing the decrease in magnetic flux. Just like before, the induced current carries positive charge carriers. But unlike before, the positive charge carriers will go to the right, which establishes a potential difference across the inductor that is actually opposite in orientation to the potential difference that we had before. Let's summarize what we know an inductor is. An inductor is a conducting coil used to store potential energy in the magnetic field it generates. An inductor will resist changes to the current running through it, generating an EMF to oppose changes in its magnetic flux. The inductance of a device depends on only the geometry of the inductor.